Section 11.8 is Lagrange Multipliers. So this is a method of finding extrema or optimal values for a function on a constraint curve or a constraint surface for dealing with three variables. So it's sort of an addition to the techniques of 11.7, but it's very specific to constrained optimization. In other words, optimizing f subject to some function g of x equal, k or some constant value like this. So finding maximum or minimum values of f subject to g equals k, g of x, y, z equals k. Now this is written for functions of three variables. Most of our exercises and examples will be functions of two variables, but the method is essentially the same for any of these. The derivation of this method, however, is a little bit easier seen for functions of two variables, and we'll discuss that down below. But to introduce the method, we need to be sure that gradient of g is non-zero on the level curve g of x, y, z equals k, where k is some constant. And then we can apply the method, and what we're looking for is all values x, y, z, input values of the function f, and some real number lambda, such that the gradient of f of x, y, z is equal to lambda times the gradient of g of x, y, z. So remember that the gradient of f and the gradient of g, each of those things are vectors. So what this is telling us is that these vectors are scalar multiples apart from each other. In other words, they point in the same direction or possibly opposite directions if lambda is negative, but they're parallel to each other otherwise. So they're aligned with one another. Now this will be a set of constraints for what's called our necessary conditions. In other words, if f has a maximum on g, this is satisfied by that maximum, as well as this. Of course, the point x, y, z has to satisfy the constraint of function g equals k. Okay, so it gives us a candidate list once we solve for x, y, z, and lambda for which this is the case. We don't actually need to solve for lambda explicitly, but we might do that along the way in some problems. What we're really interested in is x, y, and z. Now, if we have all such points, our list of candidates, then what we'll do is we'll evaluate f at each of those points that we found that satisfy the above equations. And then we'll compare the largest, or we'll find the largest on that list, we'll find the smallest on that list, and we'll have the max and min respectively. Okay, why does this method work? Well, let's consider it in two dimensions. And down below, we've got a decent drawing of what the situation is on the bottom right of the page here. So to find the extreme values of f of xy for some xy constrained to lie on the level set g of xy equals k. So here is g of xy equals k. In the picture, it's that blue curve, just kind of arbitrarily drawn. And what we consider is functions of f, which will intersect these level curves. So the key thing to realize about this situation is that this level curve, g of xy equals k, well, it's going to attain a maximum or a minimum, whatever happens to be the case here, at some point where the curve is tangent to the level curves of the function f. So it looks like in this specific case, we've got level curves f of xy equals 2, f of xy equals 4, f of xy equals 6. So with these level curves, we see where g is intersecting each one of these. Well, if g is going to have a maximum or a minimum value, it's going to occur where these two curves are just tangent to each other, because otherwise g could have a minimum, something less than 4, or our function f could have something less than 4 that's tangent to g, if this curve happened to move in just a little bit further to the left, say something like this. Okay, then that would be some minimum value on g for f that's between 2 and 4. So s value would be between 2 and 4, greater than 2 and less than 4, and on that curve g. So there would be another level curve for f, which this would pass through, and it would look something like that. Okay, so that's why this must be the case. That's the geometric interpretation of that situation. Now, if this is the case, if these two level curves of G, if the curve G is tangent to the level curve of F at this point, then we have that these two gradient vectors are parallel to each other. In other words, they must be pointing in the same direction, perhaps opposite directions. That would just mean a negative lambda, and their scale might be a little different. That's why lambda is there. But this is the statement that the gradient vector of F is parallel to the gradient vector of G down below. And that's exactly our Lagrange multiplier statement. Lambda is called the multiplier in this method. Okay, so let's work an example with this. So the first example says, use Lagrange multipliers to find the maximum and minimum values of the function subject to the given constraint. So remember what our value function is and our constraint function. Now, first thing to do, we need to find the gradient of F and the gradient of G. This is easily done. Partial derivative in each component, and we have vector gradient of F, vector gradient of G. And then set gradient of F equal to lambda times the gradient of G. What this results in is a system of equations. So in other words, this component is equal to lambda times this component, and that gives us this equation. This component equals lambda times this component, and that gives us the second equation. The third equation on that list is simply a restatement of the constraint. So this is our last equation that helps us determine x, y, and lambda. Notice that we have three unknowns, x, y, x, and lambda, and we have three equations. So we're, it's not a linear system of equations, but it's a system of three equations and three unknowns. So we may be able to find an exact solution to this, or solutions to this. There might be more than one. Okay, so now the trick is to realize that these are certainly not linear equations. So we don't have the old methods of matrix algebra and linear equations. So we have to be a little bit more clever. There's no general rules for this. You have to kind of follow your nose. A lot of practice with this helps quite a bit. And otherwise, you just have to see your way through this. It often helps to eliminate lambda. In other words, to solve for lambda in either of these two equations if we can, and then we can set these two results equal to each other through lambda. That's, remember, eliminating the parameter in calculus 2. If we have that as our situation, sometimes this leads to good things. Might not always, but sometimes it will. In this case, it does. So we end up with this result, dividing by e to the xy, because the exponential e to the xy is never 0, so it's safe to divide by on both sides. And then solving for this by cross multiplication, we've got y cubed equals x cubed. Take the cube root of both sides. So, or before doing so, we can plug this into the last constraint, right? The last equation, or constraint equation. We'll get that 2x cubed equals 16. That tells us that x is equal to 2. So we have a value of x equals 2. We can come back to here where y cubed equals x cubed, or in other words, y equals x, and we get that y is also 2. So now what we have is this is the only solution to this system of equations. It's the point x equals y equals 2, or 2 comma 2. We only know that it's an extrema of f, or a candidate to be an extrema of f. Since there's only one candidate, we know that it must be some kind of extrema. It's either a minimum or a maximum. But first we call it an extrema of f. Its value is, well, we plug the point 2 comma 2 back into our original function of f, which is e to the xy. So we plug it in, x equals y, or x equals 2, y equals 2, and we get e to the 4th as our value below. So e to the 4th, and we don't know whether or not that's a minimum or a maximum, but since this should be a local minimum or a local maximum, on this constraint curve, or really an absolute min or absolute max on this constraint curve g of x, xy, in other words, x cubed plus y cubed equals 16, then we can just search any other point on here, and we realize that 0 comma cube root of 16 satisfies this equation. So it's a point on the curve. So we plug it into f, we realize that we get 1. We have e to the 0, which is 1, which is less than e to the 4th. So it turns out that 2 comma 2 yields a maximum on the constraint curve G. So that's the way to determine whether or not it's a minimum or a maximum. If you're only asked for extrema, you don't have to determine which is which. But if you're asked to find the maximum or minimum, then you'll have to determine that if you only have this one candidate that comes about. Of course, the second derivative test is also fair enough from section 11.7, however you might care to do that. Okay, so next, this example is a little reminiscent of Calc 1, maximizing the volumes of a box with an open top. This is, in this case, a rectangular box. X, Y, and Z are the sides, and the top is open. So this top space here is actually not filled in. We want to maximize its volume, but we want it to have an area of 12 square meters. Okay, so the volume function, V equals X, Y, Z, is going to be our value function. We want to find the maximum of that, and we need the area of this thing to be equal to 12. Okay, well, we have two faces that have area xz, two faces with area yz, one face with area xy. That's the bottom face down here. Okay, so that's our value function, our constraint function, and really setting this function equal to 12 is what G actually is. So find the gradient of V, find the gradient of A. We'll list all these things and then set them equal to each other. So gradient of V equals lambda times the gradient of A, and we get this system of equations. These are from the gradient statements, gradient equality, and this is the constraint. 12 equals the area of XYZ, or for the values XYZ. Okay, so 4 constraints, 4 unknowns, and here is where things get a little bit loose. Of course, there's no one way to go about solving these systems of equations. Again, this is a nonlinear system of equations because it involves y times z. That's a second-degree term, whereas no linear equations have such terms. They're all first-degree terms. So one thing we can realize is that if we multiply each of these, this first equation times x, second equation times y, third equation times z, then the left-hand side of each of these will all be x, y, z in some commutation of the other. Okay, so we do that, so that way we can set each of these equations equal to each other, or any pair equal to each other, and work from there. We don't do anything with the constraint equation now. And so this is a nice tactic, so that way we have a more common set of terms. We can set things equal to each other. And if that's the case, we see below, the next block of work here, that we're setting 2 lambda xz. So where we're looking is this equation, 2 lambda xz plus lambda yx, or xy, or right, is equal to, so this one is equal to 2 lambda yz, 2 lambda yz plus xy. And really these should have a lambda in them that's been omitted, but it doesn't matter because they're still the same term on both sides, so they cancel out or they add to 0 and we subtract that from both sides. What we're left with in this situation is lambda xz equals lambda yz after dividing by 2 on both sides and adding and subtracting that lambda xy out. And once we have that, we can realize that if lambda were to be 0, so we have to test a couple things. If lambda was 0, then what would happen? What would be the result of this? Then x times y would be xz would be yz would be 0. In other words, all of these would be 0. And what that means is that if for any actually, don't look there. We're looking at this line. All of these would be 0. So that means that every pair, y times z, x times y, would be 0, which means that all of x, y, and z would have to be 0. That's just not feasible in this case because, well, that would be a box with no volume at all, and it wouldn't satisfy the constraint either. So we know that lambda can't be 0. The only useful thing about that is that we can divide by lambda now. Okay, so the other choice is this. When we look at this equation, is z 0 is what we would ask. If z is equal to 0, then the volume is 0. And again, we have a box with volume 0, so that's not what we're looking for. So we can make some non-zero volume box out of this. So we know that z is not 0 as well. Okay, if that's the case, we can divide by lambda z on both sides, and that leaves us with the equation x equals y. Okay, now x is equal to y, so we have a substitution. We can at least reduce the number of variables in these equations by 1. Using that substitution, x equals y, we come back to this equation, xy equals 2 lambda plus xy, and of course we'll substitute x for y in each of these components to get what we see, the equivalent equation to the right of that. And we have x squared is equal to 2 lambda times 2x. Again, x is non-zero because we don't want a box with volume 0. When we solve for lambda, in this case, we have lambda equals 1/4 x. Okay, we're just carefully picking apart substitutions here. We've got another substitution. This one now is for lambda. It's in terms of x as well, just like y equals x is a substitution for y. Now, go to the third, any one of the other pairs above, and this one's going to be probably the most useful at this point. It's xz, and that's equal to 1/4 x for lambda, 1/4 x for lambda, times 2z plus x. And now we can get an expression for z in terms of x. When we solve for z in terms of x, we have z is equal to x over 2 from that equation. So now, to recap everything, we're just sort of organically moving through this problem, finding a substitution y equals x, another substitution lambda equals 1/4 x, and a substitution z equals x over 2. Okay. Most importantly, we have y equals x and z equals x over 2. Now it's time to go to the constraint. We know a substitution for y, we know a substitution for z. We can write this entire thing in terms of x, and that's a good thing. Once we do that, we have the following, writing all our substitutions into our constraint equation, and we solve for x. In this case, we end up with x is plus or minus 2. And well, x is a length, so we only take the positive, x equals 2. And then, well, since y equals x, y is 2. And then z is 2 over 2, in other words, 1/2 times x, and x is 2, so that leaves us with z equals 1. So our point 2, 2, 1, that's the optimal dimensions of the box, x, y, z. X equals 2, y equals 2, z equals 1. The maximum volume, which we're asked for, is x times y times z, and we get 4. Now the book does this both in the Lagrange Multipliers section as an example, and it does it also in section 11.7, the min and max general methods, and it gets the same answer in both cases. The reader's encouraged to check both of those out and to try both methods. In either case, things are a little difficult, and you do have some messy algebra to do. This type of problem certainly takes some practice. Again, there are no real general rules. If you can make things all equal to the same thing, that's a good move. If you can solve for lambda, sometimes that's a good move. And that's really the most general suggestions that can be made for nonlinear systems of equations. So in the next video, we'll finish up a couple more examples. We'll see constrained optimization on functions of 3 variables, and that'll finish up section 11.8.